or so far done is we looked at statics review and then properties of material of concrete and steel. Then we looked at beam behavior, how the beam would fail, whether intention, compression, or balanced failure. Then we looked at beam design, and now I'm guessing that you guys know how to design a beam. So if I give you a bending moment, you should be able by now to find the area of steel required and turn the area of steel required in millimeter square into a bar, a number of bars. And then you're able to check if they fit into the width. You're able to find the actual effective depth. You're able to check all the code requirements in terms of area of steel minimum and also the maximum or the raw balanced, all those good stuff. So that's what we had so far. Today, I'm going to start a brand new chapter, which is about slab design. So we finished already beam design. And so you guys, so you know, we finished the beam design from one aspect, which is flexure design. So now we know how to make our beam strong in bending, but we don't know so far how to make our beam strong enough in shear. Okay, so that's so to be clear, what we've done so far is designing the beam in bending or flexure. We will do the same thing today and probably tomorrow, and I'm hoping that we can finish the discussion by tomorrow. We're gonna cover the slab design also for flexure, for bending moment. And once we finish that, probably next week, we will look at shear design. And shear design, we can apply the shear design concept on beams and slabs as well. Okay. Uh, Something you will notice, and I want to give you some heads up. You will notice today we are talking about a brand new chapter, and simply it will take us only a couple of classes for two reasons, which I will discuss in the class today. But the thing is, by now, guys, if you have already spent some in and you know what's going on, this will make your life easy. You have a good foundation and basics for the course, okay? And that's what you will feel today. I promise you, you will feel today that if you have already put some effort to understand what's going on in my class, today's class and tomorrow's class will be super easy for you because you will see there are lots of similarity between what I said before and what I'm going to say today. So today, what we will cover slab systems. So probably I need to zoom in. So slab systems. When we build slabs, we have so many systems. We'll expose you today to all those slab systems. But the thing is, slab systems is a very, very big topic, and I can tell you, you need a one year, like 2 semesters in concrete design to know how to design and detail all those slab systems. I myself back in 1990, I guess 1995, courses in concrete design, and they focus only for slab design. So you can see, you can imagine a topic that it's covered in 2 semesters. We will have to cover it here in only 2 classes. You can see the scale, huh? So because there are so many systems and every system, it has its own details for design and code requirement and detailing. But again, what we will cover is we will pick only one system among all those systems. We will teach you how to design it. And I would say to me, gives you a good foundation if you go to university and you learn more about slab systems and design. So you can see there are some names on my screen which I know that you're not familiar with. So there is something called the one way and two ways slab. Again, this is kind of a very unknown name for you for now, but I promise you by the end of today's class, you will know what does it mean one way and two ways. Really, what we will focus and cover in this class is one-way slab design. So the entire 2 hours probably most of them will focus on one-way slab design. To design one-way slab, we have two methods. One is called finite element method. Again, another vague, weird, unknown name, but you will get some information about this method. So this method, you will see, it's we use a computer software to do it, which we will not. But instead, people they kind of invented and came up with a simplified method that you can manually do, and this method called design strip method. And this is the method that we will use to design our one-way slab. And then finally, as usual, you guys know me, I always look at the theory part and then follow by numerical example, full detailed numerical example, so you guys can follow through. Okay, now let's start. So this slide here, I know it's gonna look probably a little bit weird in the beginning, but let's see when I give you some description of what's going on. Hopefully this will make you feel better. Okay. To me, probably I would say I can classify my slab into a slab with beams or slab with no beams. Slab with beams and slab with no beams. And again, that's only Tahir's classification. Probably if you look at some literature or some books, maybe they look at slabs from different perspective. But from my perspective, I classify the slabs into slabs with beams and slabs with no beams. Okay. Now, I'm gonna go one by one and to show you what's going on. I'll go one by one. You have 6 different pictures, and we'll go one by one to explain what happens between one picture to another picture and how this affect your understanding of the system. And then we will go into every one of those and give you more detail. So I'm going to start here on the top left corner. So the top left corner here, this picture here. And remember, this picture, it has two views. The top one here, this is a plan view. So this one is a plan view, while this guy on the bottom is, what do you think? This one on the bottom, what do you think? Gord, what do you think? There is a little shaded picture
Section.
below the plan view.
Section view.
That's a section, correct. That's a section, correct. So we're cutting a section through my slab over there, and that's the section over there. And you can see, guys, you can see the slab is here. So this is my slab, and you can see the slab is supported on this thing here. So this thing here is something called beams. And you can see the beam is projected to the underside of the slab. And so we call this kind of a slab, we call it one-way slab. And I know so far I cannot give you more details of why we call it one-way slab, at least for now. Okay, let's go to the other one. So again, the other one looks like we have another plan view over there. And we have arrangement of beams, not like this. We have more beams. So we added more beams on all the sides of the slab. And we also added kind of intermediate beams over there. Okay, so we still call this one-way slab. And then next one is we have another slab that we have 4 beam lines. So you can see the blue are the columns. The blue are the columns, and between the columns, we're connecting the column by beams. Okay, now I'll give you more details of the kind of the development of the idea shortly, but there are some kind of a slab that doesn't have any beams. You can see the picture here, the picture on the bottom left corner, this picture over there, you can see we have blue dots, and those blue dots are our column, and then we have the slab. You can see there is no beam. Please take a moment, identify the difference between the picture on the top left and the picture on the bottom right. I'll give you a few seconds. Try to understand where are the beams, and try to understand on the bottom picture, there is no beam. Those lines are center lines, and those lines here are center lines or grid lines and not beams. Okay. Now, what do we call this picture here? We call it flat slab or flat plate slab. Well, typically, we call it flat slab. Because simply there is nothing projected to the underside of the slab. We call it flat slab. Then what happens next is sometimes we do flat slab and we add something here. I'm going to point out to those things. So you can see here on the plan view, there are, for every column, there are two squares for every column. And it's not very clear, but if you look at the elevation, you will know better. So my slab is here, which is dark shaded. I'm going to zoom in. So this is my slab. And then there is something under the slab here only at the column location, and there is something else below this thing. You will know today that we call those drop panel and then column head. So you will get to know more details about what's going on here shortly. So we have a slab, we have drop panel, and then finally we have a column head. Now, the last system is called grid slab. And what grid slab is, it is simply, um, these boxes here, it is kind of extrusion. Um, I would say we call it grid slab, and please give me some time until I'm able to explain for you what's going in here. But really, the slab is not solid. So the slab is here, the slab is here, and it's supported on grid of small rips. I would call it not beams. I would call those one rips, and sometimes call this one rib the slab. Okay. Anyway, I know this picture is not very descriptive because it's not real, just a graphics, but soon you will see better details. Okay, let's go ahead and go one by one. So this in these slides, I'm going to go into deeper details and with actual picture from sites. Okay. So the first type of a slab, I'm going to call it a slab with projected beams. So we have a slab, and the slab will be supported on beams, and then finally the beams will be supported on columns. What you see on the right is a work in progress picture. The work in progress picture, it shows for now the reinforcement for the beams. You can see the beams are dropped, is projected down, and for sure you have to make sure that you have like the form shape will take the same shape of your beam. So we have to drop the forms to accommodate the beams, and you can see over there, this is one of the reinforcement of the beam. Okay, but it was raised, but at the end that you have to drop this reinforcement down into the form. Okay, and in this picture you don't see any slab reinforcement. There is no slab reinforcement. But where is my slab? The slab will go somewhere here. You can see this is one slab panel, and you can see all around there are some beams all around. Now, for every system, I will try to explain for you kind of the advantages and disadvantages so you guys understand the development of the idea. One of the earliest system is this one. So people ever since they say, okay, let's create a slab and then support the slab on the edges by beams, and then finally the beams will simply rest on top of columns. Where is the column? You can see the column in this picture is over there. So the vertical bars, those are column reinforcement. What's good about this system is, number one, is easy to analyze. I'm going to show you today or probably tomorrow how to analyze the one-way slab, but you will see it's not really difficult. You can do it without any PC like a laptop or software. There are some manual method that we can use to analyze the slab with projected beams. And it's good for good small areas. It is good for small areas, which means if you have a condo building, residential, there is no need for like a 10 by 10 kind of thing. And because we don't need a 10 by 10 area without any intermediate columns, so good like a slab with beams is a good option. Now, what bad about this system is beam interfere with mechanical ducts. You guys, if I go back to this picture here, look at the underside of the slab. When you look at the underside of the slab, you will see projected beams. And you guys can imagine if I need to have mechanical ducting, same as we do here in Canada for ventilation and for heating and air condition. So what happens here? You have to reroute your duct to the underside of your beam, um, you can simply make a hole inside the beam, but it requires a more detailed analysis, and that's why what people they do, they reroute the duct to the underside and hook it back to the slab again. So that's not very convenient, huh? If you think about a solid slab that has projected beams, it's not very friendly with the mechanical ducts. Number two, you can see on my slide here, it is hard to build or harder to build. Why it's hard to build? You guys can imagine if you have some experience and look at the picture here, if you wish to build this beam, looks like your form will be a little bit tricky because at some point you have to make allowance for your beam to go in. So you have to change the shape of the form to accommodate the beam. And this is very time consuming, okay? So it's harder to build because of the formworks, and it has limited span. I would say it can simply maximum, it can do 6 by 6 meter. If you have an area 6 by 6, you can make it of one slab panel without any intermediate columns. If you need something more than 6 by 6, so the slab with projected beam is not economical system. By the way, so you know, we can build anything you wish. We can make a still mix slab with projected beams 10 by 10 and make it 12 by 12. But the question is, how you can do that? You simply have to make it so thick, and when it is so thick, what happen is it will be bulky, heavy, very expensive, and so it's not good after 6 by 6 meter. And you will see in my class today, I will show you what is the smart idea if I need to make a slab system that spans more than 6 by 6 meters. So you guys, you can see here, I said here, longer spans require thicker slab, which will make sense for you, huh? Remember from our beam discussion, the your beam, the H is simply function of Ln divided by a factor, if you remember that. So the thickness of the beam or the slab, 100% correlated to or connected to the span. And so whenever we have larger span, then we require thicker slab to avoid excessive deflection. And thicker slab, what happens if you have a thicker slab? Guess what? It means I have lots of dead load. And this is on my slide. Remember, thicker slab is the slab thickness is very critical and largely affected the loads as a slab covers the entire and repeated for a number of floors. What does it mean? Guys, what I'm trying to say here is when we pick the slab thickness, we have to be very, very careful. I'll share with you why. Guys, what is the element that affects the self weight of the structure in most? Is it the column or the beams or the footing or the slab? You need to think about it. What is the element in the building that affects the self weight of the building at large? The slab or the
The s-
column
Slab.
or the
the
beams?
slab.
The
It's a
slab.
slab.
And why some of you answer the slab? The slab covers the entire area of the building, and it's repeated for how many floors in your building. Let me give you this example. Let's say you're able to save a 10 mil, only 10 mil. You know how much 10 mil? Look at my screen, my picture, my camera. So this is 10 mil, very, very little. Okay, but look at this. If you're saving a 10 mil in the floor thickness, you need to multiply this 10 mil times the entire area of your building, multiply by the how many floors in your building. Sometimes I have a condo building like in Calgary here. Sometimes we build, 20, or sometimes we have, I think, 46 or 48 floors now in the southeast Calgary, close to downtown. You can imagine if I save only 10 mil in the slab thickness, you can imagine how much saving in the weight that I did for the entire building. Very simple, you can do it now. Multiply 0.01, which is 10 mil, multiply by 24, which is gamma concrete, multiply by the area of the building, let's say 50 by 50 or even more than 50, maybe 100 by, it's, sometimes a condo building, sometimes it can be maybe 100 by 100, okay? And then multiply by 46 and you will see how much saving in the self weight you've saved. And what's the problem with that? If I simply ignore the 10 mil and it's okay, it doesn't matter, I'm very rich and I'm okay with the 10 mil extra, what happens is you're penalizing your foundation system. Your foundation system will have to carry those extra weight. That's one problem. And the other problem is whenever you have lots of self-weight, you're penalizing seismic design. I know that in this course, we don't even talk much about seismic, but seismic is the earthquakes. So the earthquake is a lateral load and it's function of the self-weight. If you have lots of self-weight, you have lots of earthquake problems and forces. Know that? Do you guys know that if you have lots of self-weight, you have a problem with the lateral loads from earthquake? Anyway, it is something probably some of you know that like let's say you are in the bus, and if you are in the bus and the bus all of a sudden breaks, what happens? So there is a tendency of people to push forward, right? Which one will push forward the more, a slim person or a chubby person? That chubby person will have tendency to push forward more because simply they have lots of inertia. This is something called inertia, which is the resistance for motion. So the same thing when seismic hits a building, if the building is light, then it doesn't have much earthquake effect. If the building is heavy, so earthquake will govern. Same as our houses. In our house is made out of wood, and wood is very light, and that's why when we design residential, typically what governs is wind, not seismic. If you design a concrete building, because the concrete is very heavy, so what happens is the seismic design will cover more than the wind. Anyway, hopefully this is I'm not going more than I should in seismic design, but here is the point. The selection of the thickness of the slab is very critical because it's going to contribute the self weight of the structure largely, which will penalize your footing design and seismic design as well. Okay, now let's look at the beauty. So this picture here, it is my second system, which is flat slab or plate slab with no beams, So please take a moment, look at the picture, and you will see why do we call it. Look at the underside of every floor, and you will see how clean. There is no projected beams in between the columns. So the slab is just a flat plate resting on top of the columns. Now, what's good about this system, as I said one more time, for every system, I will try to show you what is good and what's bad about every system. So it works very, very well, very friendly with mechanical ducting, because you can see there is no beams and I can simply pass my duct to the underside of my slab. It is easier to build. Why it's easier to build? Can anybody tell me why it's easier to build and it's easier than beams like slab with projected beams? Any idea why? Any idea why the flat slab is way easier to build than slab with beams?
Because it's easier to form that.
It is easier to form it up because all you have to do is you can see that my picture has both of them, has simply floors that's being finished already and other two floors on the top. It's still the forms are there. Look at the form. The form simply it's flat. There is only one elevation and simply it's easier to build. So one flat form, okay? And then finally, the one good thing about the spans, it can simply go for larger spans. Sometimes we can do up to 12 meter with this system. Okay. Now, what is really not good about the slab? It's harder to analyze. You will see we need, a kind of, I would say, rigorous methods, a method that is complicated. We typically use a software, not really easy to do by hand, especially if you have some curves. Look at the building. There are some curves and irregular column. There are some approximate method to analyze flat slab, but applies only if you have a very regular building like regular columns. But you can see, look at my picture, the columns are not regular. There are some half circle or quarter circle slab. So this slab must be analyzed using a software, which is not every designer or engineer is able to do that. But I can tell you we have more slab weight, so that the flat slab, it's typically thicker than solid slab with beams, so it's thicker. So which means it penalize your foundation a little bit. And then finally, which is very, very important, there is a weak connection between column and slab. Why it's weak? Because there is no beam, so the connection between the column and the slab is so weak. Okay, now let's move on. Do you see this picture? Please take a moment, look at my screen and look at this picture. Do you see what kind of failure has happened? Can you guess why this failure has happened?
Overly reinforced.
Mahdi, what did you say?
Overly reinforced. Compression failure.
That's not the reason. Like, look at the way it fails. It fails above the column, and this failure here looks like the column punched through your slab. The column punched through your slab. And as I said a minute ago, I said one of the weakest problem of the flat slab is the connection between the column and the slab is weak. And that's why we have something called the bunching shear. So the column punched through your slab, and this is what you get. Okay? And that's why.
Sir, can I ask a question?
Oh, yeah, go ahead.
Because
Jerry, are you still need to ask question?
I'm sorry, it was muted.
No, I did not mute you, but anyway, keep going.
Oh, I was saying that if the slab is only dependent on the flat plate, then when it comes to how many to several stories, so I don't know how really how the slab really can be more I mean in terms of strength, how can be the strength of the slab can be reliable in terms of just depending on the flat plate? Maybe that is why it happens like this.
It happens because of the engineer never pay attention to bunching shears. So in our design, we need to make sure the slab is strong enough in bending. And the problem is there are so many things that we have to check before we say our slab is safe. And guys, could be very, very obvious for you. What you're doing right now is steel course, correct? You are doing right now a steel course with Corwin.
Yeah.
So in the steel course, every steel member, and by the way, this is also applicable in concrete, but in steel, it's more obvious. Still, especially when you design a connection, there are so many possible ways of the connection of the steel can fail, or maybe the column can fail, or maybe intention can fail. And what you have to do is you have to make sure that your member will simply save in all those failure modes. So what happens here is the engineer that did this building was very careful when they did the bending design. So the failure of the slab in the picture is not due to bending. Look at the extreme. Look, I'm going to show you here. Look at this side here. Look at this side. Okay, so you can see here, your slab is still intact. It never failed in bending. Otherwise, this will be broken into two pieces. If you guys remember how the beam will fail in bending. Okay, so the slab here was okay in bending. But the thing is, the engineer was careless and never made a good job, never put an effort to check the slab in bunching shear. And that's why it failed in the weakest link. So the slab in bending is okay, but in bunching shear is not okay. How we do a good design? We have to make sure that the slab passes all the checks. If you forget one of the checks, maybe your slab will be good in bending, but bad in shear, so it will fail in shear. Is that clear?
Yeah.
Okay, so guys, again, bunching shear, you can see the name, it's called the bunching shear. We will not cover it in our slab design because simply we will do a one-way slab with beams, and whenever you have one-way slab with beams, simply the connection is so strong and your slab will never fail in bunching shear. However, at the very end of our course, probably sometime in end of November, end of next month, we will get to design footing, and in footing, we will see the same business, something called the bunching shear. And so in this course, you will learn about bunching shear at the end of the course, okay? But not in slab design, in footing design. Okay, now, so because the connection is so weak, so people try to, try to solve this problem. If the connection between the column and the slab is so weak, how can we solve this problem? Some of you will say, why don't we increase the thickness of the slab? If you increase the thickness of the slab for the entire area, you are in another problem. Yes, you solve the bunching shear, but you have contributed so much for the self weight of the slab. Would you agree?
Yes.
Okay, so what's smart way? Here is one of the smart ways. There are several ways. Here is one of the smart ways. So one of the smart ways, if you tell me that the connection between the column and the slab is so weak because the slab is so slim, then why don't we increase the thickness of the slab only at the column location? Are you guys following? If the slab to the beam, sorry, if the slab to the column connection is so weak because the slab is so slim. So the first answer to this is, why don't we increase the entire thickness, the thickness of the slab for the entire area? Great, but the problem is we're increasing the self weight of the slab. So what is the brilliant idea or the smart idea? Okay, why don't we increase the thickness of the slab only at the column location, only at the connection? And that's what's happening here. We have something called the drop panel. Drop panel. And where is the drop panel? I give you here three different pictures. A big picture for the entire site where you see at the column location, we drop the form. We drop the form, which means we simply increase the thickness of the slab only at the column location. There are some closer picture. You can see on the left here, another picture here. And that's again, that's not complete reinforcement. That's only work in progress picture. So you can see here, here is the elevation of the underside of the slab in between the column. And here is the elevation of the underside of the slab at the column. And you can see there is a drop. Now, another picture, which is again work in progress, not finished one. This one here is another slab, like a drop panel, So after you finish all of that, what you get, this what you get, okay? So if you look at, to the underside, so this is a picture from the on top and before the slab is poured, but after you are done, this is your finished product. Your finished product is a column, is over here, and then on top of the column there is a drop panel. So the slab here is thicker only at the column location. However, away from the column location, the slab is not that thick, and what happens? It means we have saved some self weight because we have never increased the thickness of the slab for the entire area. Okay. Now, in comparison to flat slab, so the first option, this one here, it is called flat slab. No drop panel, nothing else, just flat slab to a column. So in comparison for flat slab to a flat slab with drop panel, what happened is here, we can span for longer span, and we have less slab self weight, and then a stronger column slab connection. How about the problems? The problem is we get a little bit of ducting problem because simply you can see not very friendly. There is a drop in elevation to the underside of the slab, and also when it comes to form work, it is not as easy as flat slab. Okay, because you have to drop the slab and the form at the column location. Now, what's next is we have another level. If my span is so, it gets larger and I need a bigger drop panel, what you can do is you can do something else called column head. So you can see here, this thing here, it's called column head. And this thing here, it's called drop panel. And then finally, your flat slab is here. So flat slab that has drop panel and column head. Again, if you look at this one, looks like same thing, same deal. We have a larger span with less self-weight. We have a stronger column connection with the slab, but we have a little bit problem with the mechanical ducts, and we have more formworks to do. Okay. Now, sometimes, by the way, so you know, sometimes people, they start with a flat slab option. So they build it as flat slab. So no drop panel, no column head because it's easier to build. But sometimes after the fact, after the slab is being built, some owners, maybe the building will be sold to another owner, and the owner will do an upgrade and change the occupancy of the building, and they probably need to do some retrofitting. And this is what they do. If the slab is already built as flat slab, and later on the engineer or the designer figure out, you know what, if I change my load, no, my flat slab doesn't work. It's going to fail in bunching shear. So what happened is the designer can come after the fact and can simply do some retrofitting and simply add the drop panel and the column head after the fact. After the fact. So that's called retrofitting. Retrofitting.
Hey, Tyler,
Mm-hmm.
it might not be just a question. To retrofit the drop column or that piece there, how much difference does it, like, is it still as effective as if it was a monolithic pour like they normally are? Like, how much effectivity do you lose if you do it after the fact?
Really good question. Your question is really valid question, and you can see, if you notice in the picture, you will see number one, there is roughening. So you can see the before they add this mat, they roughen the surface of the underside of the. Do you see that?
Yeah, I've done that lots. It's just I always wondered how much, like, how effective it is compared to if it was done in the first time.
It is very effective. Now we have chemicals, we have bonding agents, and there are some epoxy. So you can see there are some vertical. I'm going to point to one of them. So hopefully you can see that. Do you see this thing here? Do you see this thing here? So
Those dowels that you're talking about that
yeah,
are,
yeah. This thing here, it's not only for holding the mat up. It does that for sure. It holds the mat up, but also what it does, it creates a kind of a doweling effect to connect the old slab with the new slab. So, and we have bonding agent. I would say that the harder, I mean, that's a very valid question, by the way. I like it, but there is also harder question, which I will add to your question, and probably some of you guys will add. How can you bore that?
Serious form work and
Huh?
maybe a pump.
usually it's just you leave a section of in all four corners of the formwork. When you get it done, you leave a hole big enough for the line pump and then just pump it in there. The
Yeah.
challenge is I guess, what's it called, consolidating it is the challenge.
Exactly. So those guys, I'll share with you. I work in one building since we're talking about this one, and every time I pass next to this building, I feel so proud, so proud. Like there is a building in the southeast of Calgary, like end of Blackfoot and Deerfoot. It's there is a couple of condo building over there, and I'm not sure if you're old enough. There is one building, it was already complete long time ago, but there is a building that stays, kind of bare for years, because simply there was some partners, and the partners, they have a problem, so they went to the court, and the construction stopped after they finished the barcade and the elevator shaft, I think. So a building that stands there, not complete, just the main floor, and I think they had second floor, and they have the five floors elevator shaft. Stayed for years. And then what happens? Finally, the court decided, and the problem solved, and the owner decided to um, simply continue construction. And what happened is, by the time they finish all the legal problems, the market has shifted, which means 5 years ago or 7 years ago, there was a need for larger units. And then 5 years later, the market has changed and needs smaller units. And what does it mean? It means the original design, the architectural original design does not work anymore. So what they did is they went back to another architect, they redesigned the whole units. But thing is, architect and structure, they are connected. Architect design and the structure design, they are connected so tightly, so tightly. And what happened is, because the architect has to redesign the building, and the structure also has to match the architectural new design, and so there was lots of magic stuff. So what happens, that was not my office design. It was a design by a company in Vancouver, and so they don't have office in Calgary here. So what they did, they say, okay, you know what? We will give you. So they will sub us, like subcontracting us as like just project management. So we do construction management. So, and that was my job. I need to go there and simply look after the construction. And so this project, that why I'm so proud of it is, when you guys build from scratch, fresh, like, it's nothing there. So you have lots of flexibility. Is not even, it's a fantastic structure, but when you do retrofitting, so things existing and where you need to cut the slab, need to add like beams, you see all those of, and you can guys can go if you can add how easy of this process compared to a fresh build. Like if you look at this picture here, how easy to do that compared to you build the same thing from scratch. So the column does not exist and the slab does not exist, and you do it as a fresh build. What do you think?
Well, a fresh build, it doesn't like it. You're probably a difference of like 5 or 6 hours to add that in there, as opposed to retrofitting it like that. You're probably 5 or 6 days by the time you prep it all, like rough it up and epoxy in your dowels, and then you gotta wait for your epoxy to cure, and then you gotta form it, and I mean, if you're up 30 some floors, then you've got other issues, right?
Yeah, I agree. Look at how Gold said it. It's in terms of time, and I can add to that in terms of technicality. Like look at technicality of roughening. So we roughen the surface. It has to be quarter inch, like 6 millimeter roughening. Epoxy. If you have done any like healthy dowels or any of those, you will see they have a certified installer. It's not like you make a hole and then you put your dowel and you're good to go. Not really, huh? If you make a hole that is way larger than the bolt or than the dowel, you're screwed. If you didn't clean the hole good enough, like from the dust, you're screwed. Lots of technicality with this one. One more thing is, are you going to use concrete? Concrete like gravel and sand and cement? Yes or no?
I think that's too much to do that.
No, I'm saying, I'm asking you. So let's say you've done the rebar successfully, so everything is okay. You've done the dowels okay. Your roughening is okay. But I'm asking you, concrete. Are you gonna use normal concrete like gravel, sand, and cement, or
That's what
this
I'm
doesn't
saying.
work?
That's what I'm saying. No, you don't do that. There is some
No, there are
substitute for
some.
that.
Yeah, no, you cannot do that because simply, uh, I'm gonna tell you how they do that. They have a hole like a core through the slab where they can pour the concrete from the next floor. It cannot be done otherwise. How can you fill the concrete to the right elevation so the old concrete and the new concrete will come together? The only way to do that is to core the slab from the top floor, and then you pour concrete from the top floor. Okay, and in this case you cannot use normal because you cannot make a 4 inch. If you can make a 4 inch, good for you. If you can make a 4 inch like core inside the slab, then that's good for you. But the thing is, we have already some rebar in the already existing slab, and if you core and cut the rebar, you're screwed as well. So you have to do x-rays, and figure a spacing in between the rebar, and then core through, and then use not concrete, use kind of a product, and those concrete it's cementing material, but not concrete, not like the normal one with gravel. There are some products from Lavarge that you can simply pour. It is very liquid, and the strength can be maybe 50 or 60 MPa. But
Are you
this
talking
one,
about Agilia?
Agilia, exactly. Agilia is one of those. Yeah, exactly. So Agilia is one. Lavarge has one product called Agilia, and I think other companies they have kind of equivalent product. But guys, what I'm trying to say here is that look at this. Like retrofitting is a whole new world, and if there is 100 contractor can do fresh build, probably there is 1 or 2 can do retrofitting the way it should be. Okay, I guess guys it's time for a break, so I'll break and I'll see you guys at 9 o'clock. Thank you.